Bismillahirrahmanirrahim. Assalamu alaikum. So now we will discuss the case where planar dynamical system x prime equal to ax is such that a has repeated eigenvalues. So in particular we will be considering matrix A of this form 0 lambda 1 0 lambda. In other words, we can say that our system is x prime equal to lambda x plus y, or you can say that y prime is lambda times y. So this is going to be the system that we will be discussing about. So the first thing that we need to do is we need to find out eigenvalues. For this matrix A, it is not hard to show that lambda 1 and lambda 2 both are equal to lambda. So therefore we say that this system has repeated eigenvalues. Because both of these eigenvalues are same, we just need to find out what is eigenvector. So for eigenvector we already know that we need to solve a minus lambda I operating on to x to be zero vector. A is lambda 1 0 lambda and minus this guy is lambda 0 0 lambda, and this all of the thing to be applied onto xy to yield 0 0, and this fellow becomes 0 1 0 0 operating onto xy, and it gives me 0 0. So this gives me y to be 0 and x to be any constant t. Therefore eigenvector v1 must be 1 comma 0, and this is the only eigenvector which is linearly independent. So we have two repeated eigenvalues lambda 1 lambda 2 to be lambda, and our eigenvector is 1 0. And you can recall your ordinary differential equation to show that the solution to x1 will be equal to alpha times e to the lambda t times v1 0. And you can apply method of undetermined coefficients to show that the general solution to the general solution to x prime to be ax, where a is this lambda 1 0 lambda, can be written as x of t to be equal to alpha times e to the lambda t times 1 0 and plus beta times e to the lambda t times t 0. So this is going to be the general solution to the system we have. Now we need to discuss what happens in as we move over time goes to infinity. So we will be discussing it into the cases. So the case 1 is, so lambda 1 and lambda 2 are equal. Assume that lambda, which is lambda 1 lambda 2, this is lambda, suppose this is less than 0. Now our solution is given by x of t equal to alpha times e to the lambda t 1 0 plus beta t e to the lambda t times beta e to the lambda t. This was the solution. What will happen is t will go to infinity. In other words, when you apply the limit, because lambda is less than 0, so for sure this will go to 0. In other words, this vector will become 0 0. Indeed, this will also go to 0. Why? Because this e to the lambda t is lambda is negative. Okay, what will happen with this term? So like, we need to see what will happen if t goes to infinity. T e to the lambda t, really we want to see what happens to this. You can write this as t goes to infinity, t over e to the minus lambda t. Now if you are applying t goes to infinity, then this is infinity, and e to the minus lambda, because lambda is negative, so minus lambda is positive, so this will also be going to plus infinity. So plus infinity over plus infinity is indeterminate form, and we can appeal to L'Hopital rule. So applying L'Hopital rule, we can get that this is going to be 1, and this is minus lambda e to the minus lambda t. Now if you apply this t goes to infinity, then the lower part is going to be infinity, and which gives me 0. Therefore this will also be going to 0. What we concluded from here, it says that when lambda is less than 0, in that case limit t goes to infinity of x of t, in other words the general solution goes to origin. So in other words, if lambda is less than 0, then all of the trajectories will be moving towards the origin, and in fact they will be moving towards the origin tangent to this vector 1 0. Now we can see, for example, we can take this example let's say I can take lambda to be minus 2, for example. Then system is going to be 8 x prime to be minus 2 1 0 minus 2, and then this is xy. In other words, the system is x prime is minus 2x plus y, and y prime is minus 2y. We can plot this on phase portrait plotter and see that trajectories will really be moving towards 0 0 origin. So let's see what happens. So this is the system, and you can realize that the trajectories are moving towards, directed towards origin, and they are tangentially moving with 1 0, in other words the x-axis. Okay, so they are moving tangentially with the x-axis towards the origin. Okay, so and you can realize that 0 0 is a fixed point already for such planar systems, and this is stable. Why? Because all the trajectories are moving towards 0 0, and every trajectory that will be starting in the neighborhood of 0 0 will remain inside it. In other words, sufficiently close trajectories to 0 0 will remain close to 0 0. So 0 0 is stable in the case when lambda is less than 0, and 0 0 can also be said as the attractor of the trajectories, because all the trajectories are attracted towards 0 0 as t goes to infinity, and we assume that lambda is less than 0. So now if we see lambda is greater than 0, I hope you have guessed what will happen. Now consider the case 2, where lambda 1 lambda 2, which is same lambda, and let's say now it is positive. Then we know that x of t solution is given by alpha e to the lambda t 0 plus beta t e to the lambda t times beta e to the lambda t. Now if lambda is greater than 0, then as t will go to infinity, what will happen to all of these terms? This term will also be, moving towards plus infinity, or maybe minus infinity, depending on this alpha. In other words, this will be moving away from 0 0. So either it's minus infinity or plus infinity. This term will also be moving away. This term will also be moving away. So in other words, the trajectories will move away from 0 0 origin for lambda greater than 0. When lambda is greater than 0, the x of t, the solution trajectories will be moving away from 0 0. We can quickly go towards example of this. For example, I can consider lambda to be now plus 2. So my system should be x prime to be 2 1 0 2 and xy. So x prime should be 2x plus y, and my y prime should be 2y. Okay, so I can plot this and show you that the trajectories are really moving away from 0 0. So let's see what is. So you can realize that the trajectories are moving away from origin. They are directed away from origin. So you can see that. Though they are moving away along 10 x-axis, but they are moving away. Okay. So you can also conclude that in this case, 0 0, which is origin, is unstable, or it is repeller of the trajectories. Okay. So let's conclude everything. For the system x prime to be ax, with a being lambda 1 0 lambda, number one, if lambda is less than 0, then 0 0, which is origin, is stable fixed point, and all trajectories tend towards 0 0. And if lambda is greater than 0, then 0 0 is indeed unstable fixed point or equilibrium point. You can write 0 0 is unstable equilibrium point, and trajectories tend away from 0 0. When I say away or tend towards, I'm talking as t goes to infinity. In other words, in long run. So your 0 0 in this case is attractor, and in this case it is repeller. Thank you.